this video, we're going to look at chapter 23, part 2. So in part 2, we're going to talk about the motional electromotive force, electric motors, and transformers. So now we're going to get into section 23.3, which is the motional electromotive force. So we've already said before that the magnetic flux can be defined by this equation. Is the strength of the magnetic field times the cross-sectional area times the cosine of the angle between the direction of the magnetic field and the normal to the area. So we said that if the angle is 90 degrees, then because cosine of 90 degrees is 0, the magnetic flux is just going to be 0. So we get maximum flux when the angle is equals to 0. We also said that a change in magnetic flux is going to induce an electromotive force that is called the Faraday's law. So this is an example here that we can use to generate a current, to induce a current. It's called the motional electromotive force. So basically, what this example shows me is that you have magnetic field lines that are going into this loop. But if you look at this loop here, it's made up of 4 wires. So there is a wire at the top, the one on the left side, the one at the bottom, and the one at the right. So this is the one that can move. So because this can move, this piece of the wire here can move, it means that the area of this loop is going to change. So as this area is going to change, as this wire moves to the right, then the flux is going to change. And we know that a change in flux is going to induce an electromotive force or a current in the wires. So this is a magnetic field that is pointing. It's a cross. It means that it's pointing into the paper. Then you have this segment of the wire moving to the right. So this will cause this area. So this area is going to change. Now because the magnetic field is pointing into the paper, it means that the current is going to be induced in such a way that the current is going to flow in the counterclockwise direction. And the reason is because, again, we said that Lenz's law can be used to determine the direction of the induced current. So if the current is moving in the counterclockwise direction, then it means that the magnetic field that is generated by the induced current is going to be pointing out of the paper. So this is so if you look at this picture here, so using the second right hand rule, if I know what the direction of the current is, I can use my fingers here to get my direction of my magnetic field. So it means that the induced magnetic field has to point in such a way that it should be opposite to the magnetic field that is causing the current. So this is called the Lenz's law. All right. So again, one application of motional electromotive force is that it can be used as a power source. So again, as you can see here, so you have a magnetic field going into this loop, but as this wire is moving to the right, the area of the loop is changing. And so because the area of the loop is changing with time, it means that the magnetic flux is changing with time, and this will induce a current that flows in the counterclockwise direction. So now we can do a little bit of mathematics here to derive some equations. So for example, we already said that the electromotive force is given by this equation, is a number of turns times the change in the magnetic flux as a function of time. So in this example, the magnetic field itself is not changing. It means that the only change in the electromotive force comes from the change in the area as a function of the change in the time. So we can say that the change in the area is just the length times the change in x. So again, if you look at this picture here, the change in the area is the length times the change in x. So this is the change in area right here. So if I substitute the change in area, which is the length times the change in x, and I divide that by the change in time, then I can derive, because I know that the change in x over change in time is just the speed or the velocity of this wire right here. So it means that I can derive this equation here. So the electromotive force is just the strength of the magnetic field times the length of the wire times the velocity of the wire. So if I know the strength of the magnetic field, I know what the length of the wire is, and I know what the velocity is, I can calculate the induced electromotive force. So again, we notice that in this example here, theta is just equal to 0 because the magnetic field is always at 90 degrees with respect to the area of with this surface area. So it means that the angle is equal to 0, and when the angle is equal to 0, the cosine is equal to 1. All right, so now we're going to look at one example here. So in this example, so we're going to calculate, so at what speed must this wire here, or the sliding rod, so at what speed should this rod be moving in such a way that I can generate an electromotive force of 1.0 volt in a 1.30 Tesla field that is directed perpendicular to the rods and into the page, given the rod's length is 31.5 centimeters. So in this equation here, I want to just calculate the speed. So the first thing that I want to do is to write down all the quantities that are given. So it tells me what the electromotive force is. It's 1.0 volt. The strength of the magnetic field is 1.30 Teslas. The length is 31.5 centimeters, which is 0.315 meters. Then because I know that the induced EMF is given by the strength of the magnetic field times the length times the speed, so I can substitute this equation here to get the speed is equal to the electromotive force divided by the strength of the magnetic field times the length. So if you do that, you get about 2.44 meters per second. All right, so now we're going to talk about one more application here. So this is section number 23.5. So again, I think we've already discussed a little bit before about the difference between an electric motor and an electric generator. So basically, an electric motor uses current. So it starts with electric current, and then as the current goes through a loop in the presence of a magnetic field, the magnetic field is going to generate forces, and these forces will create a torque that is going to rotate this loop. So basically, I'm converting electrical energy into mechanical energy. Now, a generator does the opposite. So it converts mechanical energy into electrical energy. So this is an example right here. So it takes energy from the wind and then uses that energy to rotate a magnetic field, to rotate magnets. And those magnets are going to be connected to some coils, the conductive coils. And because the magnets are going to be spinning, it means that this will be generating a magnetic field that is changing with time. And the changing effect of the magnetic field is going to induce electric currents in the conductive coil. So again, the generator simply takes mechanical energy and converts that energy into electrical energy. All right. So this would be an example here of an electric generator. So here, the picture on the right here, so what we're doing is that we're just like mechanically rotating this loop. So as we rotate this loop in the presence of this magnetic field, what happens is that the area, so as this is going to be spinning, so this is a loop, as the loop is spinning, the area that the loop is going to make with the magnetic field is going to change. And so because the area is going to change, it means that I'm going to have a change in flux, and the change in flux is going to induce a voltage or a current in this loop right here. So again, this is called the Faraday's law. So the picture that you see on the left side is just an example. So this is this is an example of a steam turbine generator. So again, this works by using steam. So the steam is produced by burning coal, and then it's going to be used to spin the blades, and then those blades are connected to a magnet, and the magnet is connected to some conducting coil, such that as the magnet is rotating, it's producing a change in magnetic field, and the change in magnetic field is going to induce a current in the conductive wires. All right, so this is one example that we want to look at. This is example number 23.3. So we're going to calculate the electromotive force induced in a generator coil. So the first thing that I want to do is that so we have a generating coil, and then it's going to rotate through 1/4 of a revolution. So 1/4 means that it's going to go from theta equals to 0 to theta equals to 90 degrees in 15.0 milliseconds. And then it tells me that this has a total of 200 turns and a radius of 0.5 centimeters, and is placed in a magnetic field that has a magnitude of 1.25 Teslas. So we notice that when this generator coil is going to rotate through 1/4 of a revolution, it means that the area is going to go from 0. So theta is going to go from 0 to 90 degrees. So as theta goes from 0 to 90 degrees, it means that I can calculate, so the change in the cosine of theta is just going to be -1, because cosine of 90 is 0, cosine of 0 is 1. So if you take cosine of 90 minus cosine of 0, you get -1. And because I can calculate the cross-sectional area using pi radius square, then I can use this equation here to calculate the change in the flux. And if I solve this equation, I end up getting a value of about 131 volt. So that is the EMF induced, again, just by substituting. So N, I know what N is 200. I know what the area is, I know what the strength of the magnetic field is, and I know what the change in time is. I can substitute all those values in here. All right, the next thing that we're going to talk about to wrap up this section is transformers. And basically what transformers does is that they simply take a voltage and convert it from one value to another. So for example, this is transformers that are used in a power plant. So you can see that the voltage is produced at 12 kilovolt here. So, and then you step this up to about 400 kilovolt. And then for domestic applications, we only need to get about 240 volt. So you step it up here, and then you step it down right here. This is also other uses of transformers. For example, the transformers that are used in a cell phone. So for example, you can have a cell phone that only needs about 3 to 12 volt. So you would use a transformer that would take about 120 or 240 and step it in the range of about 3 to 12 volt. All right, so the transformer equation here simply tells me how I can calculate the voltage. So basically you have the primary coil and the secondary coil, and this equation tells me how the voltage in the secondary and the voltage in the primary are related. So NS is the number of coils in the secondary, NP is the number of coils in the primary. So for example, if NS is greater than NP, then it means that NS over NP is greater than 1, and then you can multiply that by V primary. It tells me that V secondary is going to be greater than 1. I can also derive a similar equation for current using this equation. So I primary over I secondary is just equals to the number of turns in the secondary divided by the number of them.